Well, I'll just go with what I got here. Ferrari's other square. This is from Lodovico Ferrari way back in the 1500s. Um, he was mentioned in Guillermo Cardano's Ars Magna in relation to solving a quartic polynomial. And in that process, he developed something called Ferrari's square, which I'll show you in a little bit. But his game plan was to set two squares equal to each other. And as I looked at Ars Magna, I couldn't find that other square. And I think that's one reason why the problem I'm going to talk about has been hard to solve for since it was published 500 years ago. Uh, this is I'm going to call Decoy's story problem. How can you take a 10 unit length and split it into three co-proportional parts where the product of the first two gives you six? So if you let the middle one be x, in order for the product to be 6, the first one's got to be 6 divided by x. And then to go from 6 over x to x, you get a constant of proportionality of x squared over 6. So the third one must be x cubed over 6. You put all that together and you have the equation 6 over x plus x cubed over 6 equals 10. Hopefully you're following me okay. If you clear the denominators, you get what I refer to as Decoy's quartic, uh, and that's the first equation I have presented. Now, what I'd like you to do is look at that left side and see, well, what do we have to do to make that square of a binomial in x squared? Well, one thing you could notice is that if we had 12x squared instead of 6x squared, then it would be a perfect square. Um, you'd get x squared plus 6, that quantity squared. That's what they did in Ars Magna. We're going to do something just a little bit different. If instead of adding 6x squared, you just simply subtract 27, you get 9 plus 6x squared plus x to the fourth, and there you go. You got another perfect square. X squared plus 3, that quantity squared. Now, I chose to take a different path on this problem than what I had originally published uh, earlier in June. Um, just to show some differences and similarities between doing this a little bit different. So the approach of subtracting 27, that's not an Ars Magna, but it works out just fine. So this is actually a photograph of Ars Magna. It's just amazing what you can look up in the library around here. But I'd like you to notice that each side is broken up into three pieces. And if you think of the first piece as x squared, the next piece as 3, and the final piece as d, you could actually use that square to reason out that when you take the area of the whole square that I have on the left side, you get the area of x squared plus 3 quantity squared. And that takes care of most of the rectangle, but you've got a few other bits that I've got dragging out the side, and then taking up the end of it is d squared. Yeah, notice I have the equation number 3 and 4 there. In case you're following with my paper, those are the equation numbers that I had in the paper. They've got no other significance. So anyway, you look at that first term, x squared plus 3 quantity squared. Well, we knew that's 60x minus 27. So make that replacement. And then if you simplify the last equation, number 4, you've got it in terms of x squared, then x, and then the constant term, or in standard form. So the left side's the area of Ferrari square. How about the right side? How is that a square? Well, it's a square if you have a double root. And that occurs when the discriminant is 0. And you can actually solve that to get another condition for having a double root. And actually, AC equaling B over 2 quantity squared is the way that Cardano looked at it in Ars Magna. Now, if you do that and calculate when is the what corresponds to that equation and simplify, I've done that for you, and you get this polynomial P of D, a cubic. Now, one of the things that I'm trying to share with you today is a technique for solving equations that involves a Chernhouse number, and you'll see what it does for us in a little bit. But in this case, we came up with a Chernhouse number of -2. It's the negative of the second leading coefficient divided by the first coefficient times the degree of the polynomial. Now, we're going to use synthetic division to divide by t minus -2 or t plus 2. We're actually moving the polynomial to the right 2 units. So we put the coefficients across the top line and start working with the synthetic division. Can you see my pointer? I'll take that as a yes. You
Yes, perfect.
multiply the 1 by -2, add to get 4, multiply by -2, you get -8, add to get -35, multiply and add, and you get -380. If you watch the action of that 2 as you repeat the synthetic division, you can see how it zeroes out the second term. That simplifies it a great deal. Oftentimes that's called reduced. I like the term centered for that particular action. So anyway, what we get out of this is that the equation of the polynomial, when it's shifted to the right 2 units, is d cubed minus 39d minus 380. Um, so, well, I got off track here. Here we go. Excuse me. So there is a formula that rather famous one that is in Ars Magna. This is an equivalent one that I've constructed here. But if you have a reduced cubic, you get one solution by substituting in the values for P and Q. When you use -39 and -380, that works out to be the sum of the 2 cube roots that I'm showing you in equation 8. And to get the solution to the original polynomial, you just add -2 to it, and that's all. That's a root of p of d here. So when d is this value, we're going to get a square. Um, this particular lemma I didn't even include when I first wrote the Scrubby Plant. I thought it was obvious, but basically, if you have a double root, uh, you just have a transformation where a is the only coefficient left. So ax squared plus bx plus c is the same as a times the quantity x plus b over 2a, that quantity squared. And from there, you can take the square root of that 2D and you get uh, for what I'm calling Ferrari's other square. So two squares are equal when the roots are equal, which gives you the equation on the top. And if you simplify it, you get it on the bottom. Notice again, I've got the coefficient 1, negative square root of 2 dx, and then kind of an ugly constant term. And 13 is the equation number for this one. So again, I took those coefficients and lined them up at the top of um, synthetic division or repeated synthetic division table. We've got a Chernhouse number of d over 2, and you can see it's zeroing out there. And so basically, we're looking at an equation that's x squared plus a constant equals 0, and that is pretty easy to solve. X is the Chernhouse number plus or minus the solution to the centered curve. I haven't been able to find that in print anywhere else, but there you go. Um, Another case when you can get squares equal is when you have opposites. So I tossed a minus sign in there. And when you simplify, it's got some similarities to the original, but again, I'm looking for the coefficients of the three terms here, square term, linear term, and the constant term. And the Chernhouse number is negative of what it was before. And when you work it out, we have a simplification of x squared plus 0x plus that ugly constant, which all the terms are positive, and when they get moved to the other side of the equal sign, they're negative, and extracting a square root involves our friend I here, the square root of negative 1. Um, so those are the complex solutions, and I don't think anyone's seen those in print before. I didn't include them with my paper, the Scrubby Plant. Um, I have a tendency to rush through stuff, so I added one more thing here at the end. I really got inspired when I tried this technique with the quadratic formula. If you work out the Chernhouse transformation with it, you see you have a 0 and then familiar looking fraction at the end. And it's not too hard to get from that a form of the quadratic formula. It's the Chernhouse number plus all the solutions to the centered column. When I saw that, I suddenly realized that the quadratic formula has a more mathematical presentation than the normal one, and that's what motivated me to work on this research. Like I said, I have a tendency to rush through. I did want to show where I was able to find Ruffini's original 1804 work. I could check it out from the library, and after paging through it, I found first synthetic division for the first time in 1804. Thank you, Paolo Ruffini. And a few pages later, he was actually showing this horizontal transformation technique that I used on it. But as I look back on trying to figure out why did this take 500 years, I got to tell you, I'm totally mystified. At one place, I thought, well, maybe it's that horizontal transition lemma, getting that A in there, but for me, I thought it was obvious, but you got a proof of it anyway. So, I believe that's all I have to share with you. So I'm ready to field questions if you have them.